Hi, and welcome back to Tactical DevOps. I'm Joe.
And I'm Jane. Today we are taking a look at Kubernetes troubleshooting.
Yeah, and I want you to imagine the scenario for a second. It is, well, it's 3 in the morning.
The worst time.
Right, exactly. Your pager is just screaming on the nightstand. You grab your laptop, wipe the sleep out of your eyes, and, pull up your dashboards.
Oh, I've been there.
Yeah, we all have. The production checkout service for your e-commerce platform is just completely down. Thousands of dollars are like draining out of the company by the minute.
So stressful.
It really is. So you open your terminal, you punch in a command, and you are just staring at an absolute sea of red alerts. Nodes are dropping, pods are in a total death spiral. Where do you even begin? Like, what is your very first move?
I mean, it is the ultimate nightmare scenario for anyone running production systems. And if you don't have a systemic, highly structured mental model for how to debug a distributed system, that 3 a.m. panic is going to lead you to just start randomly restarting things.
Which usually doesn't end well.
It almost always makes the outage worse, you know?
Yeah, which brings us to the mission for this deep dive. We are taking you through the absolute trenches of Kubernetes troubleshooting today.
The fun stuff.
Exactly. And let me put some stakes on this, because if you are preparing for the Certified Kubernetes Administrator exam, the CKA, this specific domain, troubleshooting, is the largest chunk of the entire test.
It's huge. It's the massive 30% of the material.
Right. Cluster failures, application crashes, networking black holes. But honestly, even if you never plan to take a certification exam in your life, you need this.
You really do.
Because knowing these scenarios is the difference between a 5-minute surgical fix and a multi-hour system meltdown where you end up having to explain to your boss why the database literally evaporated.
Yeah, and when a cluster starts throwing errors, you have to remember that it rarely fails in just one isolated way.
Because it's too complex for that, right?
Exactly. Kubernetes is a highly complex, layered, distributed system. So, that means a symptom you observe at the very top layer, like an application pod crashing, might actually be a symptom of a failing node beneath it.
Or a storage thing.
Right, a storage bottleneck somewhere else, or even a completely corrupted control plane. We are going to break down every single one of those layers today.
I love it.
We're going to build the exact checklist you need to isolate problems mechanically, without the guesswork.
Okay, let's unpack this, because before we go running into the burning building, we need to know what is actually in our fire extinguisher toolkit.
That's a great way to put it.
Right. Like, as a first responder to a cluster outage, there are certain foundational commands you just have to know by pure muscle memory. We are calling them the Big Five.
The essentials.
Yeah. Let's start with the absolute first step. You see a broken pod, you see a broken node, you see a broken service. The reflex command just has to be kubectl describe.
Oh, absolutely. That is your primary diagnostic tool. When you run kubectl describe against any object, you are basically pulling up its complete medical chart.
It's not just a quick summary.
No, not at all. It doesn't just give you a simple running or failing status.
Yeah.
It dumps out the entire state of that object. You get the labels, the annotations.
The IP addresses, right?
Yeah, the IP addresses, the exact resource requests and limits, the specific node it was assigned to, everything.
I always think of standard get commands versus describe commands, like rounding a hospital ward.
Oh, I like that analogy.
Right. So if I run kubectl get pods, it is like walking past the patient's room and seeing they're lying in bed. Okay, good to know. But running kubectl describe is walking into the room, picking up the clipboard at the end of the bed, and reading their entire history.
That's exactly it. And the most important part of that clipboard is usually hiding at the very bottom of the terminal output, right?
The events list.
Yes. That bottom section of the describe output is a chronological log of everything the Kubernetes control plane has recently done to that specific object.
So, if it couldn't schedule a pod.
Exactly. If the scheduler couldn't find a node for your pod, it is in those events. If the node's agent had trouble mounting a network volume, it is in those events. It is the immediate context you need to understand the failure.
Okay, so that is our medical chart. Moving down the toolkit, we have tool number 2, which is kubectl logs. Now, my gut instinct says, this is pretty self-explanatory, right? I am checking the container output.
Right, that's the general idea.
If my application is throwing a Java stack trace or a Python error, I just read it there.
You do, but there is a mechanical nuance to understand about how Kubernetes actually handles those logs.
Okay, what do you mean?
Well, kubectl logs is specifically capturing the standard output and standard error streams from the primary process running inside that containerized application.
So it's purely application level.
Yes, pure application-level debugging. But if your pod is constantly restarting, like crashing, coming back up, crashing again, running that command, might just show you a blank screen.
Wait, really? Why blank?
Because the new container hasn't had time to fail yet.
No.
Just spun up.
Oh, that is a trap. You run the command on a restarting pod, see nothing, and just assume the application is fine.
Happens all the time.
So how do you get around that?
You append the -- previous flag to your command.
-- previous.
Exactly. That tells the cluster, hey, don't show me the standard output of the container that just started 3 seconds ago. Dig into the graveyard and show me the standard error of the container that died right before this one.
And that's where the error is.
Yeah, that is usually where the fatal exception is hiding.
That flag is a lifesaver for sure. All right, tool number 3 is kubectl exec. This is for when reading the logs isn't enough and you actually need to, step inside the crime scene.
Because sometimes an application just fails silently. The logs are totally empty, but the web server is returning a 500 internal server error.
Yeah, the worst kind of error.
Truly. Or maybe you need to verify if a specific configuration file actually made it inside the container's file system. Or you need to run a network ping from the perspective of that specific pod to see if it can reach a database.
So kubectl exec lets you do that.
Yeah, it allows you to open an interactive bash or shell session directly inside that running container environment.
It is essentially teleporting inside the pod to look around.
Exactly like teleporting.
But hold on, if we are trying to figure out why the cluster is failing, why are we poking around inside the container's isolated file system? Isn't that the developer's problem?
You'd think so, but a massive percentage of perceived cluster failures are actually just application misconfigurations.
Really? Like what?
Like a developer might claim the Kubernetes network is completely broken. But when you exec into the pod, you realize their application is trying to read a database credential file from a directory that doesn't even exist.
Oh, I see. So it's not the network at all.
Right. Teleporting in lets you prove where the boundaries of the problem are.
Fair enough. Prove it isn't the network before you start, tearing down the entire network.
Exactly.
That brings us to our 4th major concept in the toolkit, which we touched on briefly earlier, and that's events. We mentioned they show up at the bottom of the describe output, but you can also query them cluster-wide, right?
Yeah, you pull them for the whole cluster.
So what I am trying to wrap my head around is how events structurally differ from the logs we just talked about.
Well, think about the perspective. Logs are the internal monologue of your application. The application itself is writing them.
Okay, so the app is talking to itself.
Yeah. Events, on the other hand, are the external timeline of what the Kubernetes infrastructure is doing to your application.
Oh, I like that. So if logs are the diary entries of the suspect, events are the surveillance camera footage from the hallway outside their room.
That is a brilliant way to conceptualize it. Events show you the mechanical infrastructural actions.
Give me an example.
Like when the control plane scheduler decides to place a pod on node number 3, that generates an event. When the agent on node number 3 pulls the container image from the internet, that is an event.
And what if something goes wrong?
If node number 3 runs out of memory and violently kicks your pod out to save itself, which is an eviction that generates a critical event.
So logs tell you why the code broke, but events tell you why the cluster decided to intervene.
Exactly.
Logs say, I, the application, am struggling to connect. Events say, I, Kubernetes, have terminated you for using too much RAM.
Yep, spot on.
Okay, that distinction is super vital. Now, the final tool in the Big 5 toolkit is journal-ttcl. And I have to push back here.
Well, here we go.
Look, if I already have kubectl logs to see the application's diary and I have events to see the cluster surveillance cameras, why on earth do I need to dig into raw Linux system service logs with journal-ttcl?
It seems like a lot, I know.
It feels like stepping out of Kubernetes entirely.
What's fascinating here is that it does feel like stepping out, but that is precisely the point. You have to remember that Kubernetes is not some ethereal magic floating in the cloud.
As much as we pretend it is.
Right. It is a piece of software that runs on actual physical or virtual servers. It runs on a Linux operating system.
Okay, true.
And the specific agent that makes a raw Linux server act as a Kubernetes worker node, which is the kubelet, runs as a standard system service managed by systems on that host OS.
Ah, so it sits below the container level.
Exactly. It is the bridge between the bare metal server and the abstract cluster.
And if that bridge collapses...
If the kubelet process itself crashes on the Linux server, it cannot report its status back to the control plane. It cannot pull container images. It cannot generate those helpful events we just talked about.
Wow.
From the cluster's perspective, that node just goes completely dark.
And if I try to run my fancy kubectl commands against a pod on that dark node, what happens?
The command will likely just hang, or time out, or maybe return stale data, because the agent responsible for answering that command is dead.
The surveillance cameras are turned off.
Exactly. In that scenario, the Kubernetes tools are useless. You have to bypass the cluster entirely, SSH directly into the raw Linux server, and run journal for all -u kubectl to read the operating system logs and find out why the primary agent died.
It is the ultimate fallback mechanism. When the high-level orchestration fails, you drop down to the bare metal Linux administration tools.
You have to get your hands dirty.
Okay, we have our first responder toolkit prepped and ready. We have the medical charts with describe, the application diaries with logs, teleportation with exec, the surveillance cameras with events, and the bare metal fallback with journal prickle. We are ready to step into the fire.
Let's look at the layers, starting from the ground up.
Yeah, the logical first place to investigate when a cluster is acting erratic is the foundation it sits on, right? The nodes?
Definitely the nodes.
Because if the foundation is crumbling, you can have the most beautifully written, perfectly optimized microservice in the world, and it will still crash. If the server your applications are running on runs out of physical disk space, you are going down with the ship.
A cluster is only as stable as its underlying compute capacity. And Kubernetes is actually very proactive about reporting the status of this foundation through a mechanism called node conditions.
Node conditions, what are those exactly?
They are continuous health checks that every single node evaluates and reports back to the control plane.
Got it. And there are 5 critical conditions you need to memorize, right? The first one is pretty straightforward, which is ready.
Yes, ready is what you want to see.
That means the node is healthy, the network is functioning, it is accepting pods, and, life is good. But then we dive into the pressure conditions. We have memory pressure and disk pressure.
The dreaded pressure conditions.
Now, those seem pretty literal, but what are the actual mechanics triggering them?
Well, they are literal, but the thresholds really matter here. Memory pressure doesn't mean the node is completely out of RAM.
Oh, it doesn't?
No, it means the available memory on the Linux host has dropped below a specific configured eviction threshold. The node realizes it is dangerously close to a complete kernel panic, so it flags this condition to tell the control plane, hey, stop sending me new workloads, I am suffocating.
Makes sense. And disk pressure operates the same way.
Similar concept, yeah. Disk pressure usually means the node's root file system, or its image file system, which is where it stores all the downloaded container images, and the running container logs is filling up rapidly.
So if it hits a limit, it panics.
If that disk hits 100%, the entire node freezes. So the kubelet throws the disk pressure flag to prevent a total failure.
Okay, those make intuitive sense. But then there's the third pressure condition, which is PID pressure. PID pressure.
I have to be honest, every time I hear that, it sounds like a plumbing issue, like a valve in the server room is about to burst or something.
Yeah.
What exactly is a PID and why is it under pressure? It is a resource plumbing issue, in a way. PID stands for process ID.
Process ID. Okay.
You have to step back into Linux kernel mechanics for a second. Every single time a program runs on a Linux system, whether it is a massive database or a tiny bash script, the operating system assigns it a unique numerical process ID.
Right, so the kernel can keep track of what is running.
Exactly. But the Linux kernel has a maximum limit on how many process IDs it can track at any given time.
There's a hard limit.
Yes, this is governed by kernel parameters and a feature called dgroups. PID pressure means the node is running out of available numerical IDs to hand out.
How does that even happen? Are people really running 60,000 separate applications on one node?
Usually it is a bug. It happens when a poorly written application inside a container gets trapped in a loop where it keeps spawning new child processes, often called a fork bomb, but it never cleans them up.
Yikes. So they just pile up.
Yeah, those zombie processes just sit there, each holding on to a unique PID. Eventually, the node runs out of IDs.
And what happens then?
When that happens, the entire server locks up because the OS literally cannot launch a single new process, not even the process required to let you log in and fix it.
Wow. So one badly written script can exhaust the node's ability to even count processes, bringing down the whole server? That is terrifying.
It really is.
And the final condition is network unavailable, which simply means the network routing for that node isn't configured correctly, so it can't talk to the rest of the cluster.
Right, it's isolated.
So to translate this to the real world for you listening, if any of those pressure conditions hit or the network breaks, the node transitions out of the green ready state. It becomes not ready.
Yes, not ready.
But what does a not ready node actually look like to the end user browsing your website? Do they suddenly see a giant 404 error screen?
Well, if your cluster is architected correctly for high availability, the end user shouldn't notice immediately.
Okay, that's good.
Right. When a node goes not ready, the control plane gives it a brief grace period, usually around 5 minutes.
But if it doesn't come back?
If it doesn't recover, the cluster actively terminates the pods on that broken node and reschedules them onto healthy nodes.
But for you, the administrator,
It is a massive alarm bell. You just lost a huge chunk of your compute capacity. If you ignore it and a second node goes down under the increased strain, then your users start seeing downtime.
let's run a scenario then. Your pager goes off. You run kubectl get nodes, and you see a node not ready. You are the first responder. What is the exact diagnostic checklist?
Step 1, we reach for the medical chart. You run kubectl, describe node, and append the node's name. You scroll down past the IP addresses and the labels, straight to the condition section we just dissected.
Checking for those pressure flags.
Exactly. Is it flagging memory, disk, or PID pressure? If it is, the node is telling you exactly what is wrong and you know what resource needs to be cleaned up.
But what if I look at those conditions and instead of saying true or false, the status just says unknown? Like what if the control plane literally has no idea what is wrong with the node?
That is a critical clue. If the state is unknown, it means the kubelet agent on that specific server has stopped phoning home to the control plane.
It went totally silent.
It has gone silent. So step 2 is to bypass the cluster entirely. You establish an SSH connection directly into that raw Linux server, and you check the status of the agent itself. You run system status kubelet.
And if that command returns an output saying the service is stopped or it failed with an error code, we move to step 3.
Right. Step 3 is grabbing the system logs to figure out why it crashed. You run journal-dash, you kubelet. This will dump the standard error of the agent.
What kind of errors would we see there?
Maybe it lost its security certificates and got locked out of the cluster. Maybe someone pushed a bad configuration file update that broke the agent's initialization sequence. The logs will tell you.
Okay, so we checked the node status from the cluster's perspective, we checked the agent's status on the server, and we read the agent's logs. What if the kubelet is actually running fine, but the node is still not ready? What is step 4?
Step 4 is checking the container runtime. The kubelet is the manager of the node, but it doesn't actually run the containers itself.
It doesn't.
No, it delegates that physical execution to a container runtime, something like containered or CRIO, communicating over an interface called the CRI.
Oh, I see. It is a chain of command? The control plane gives orders to the kubelet turns around and gives orders to the runtime?
Exactly. And if that container runtime daemon is frozen or misconfigured, the kubelet will report a not ready state because it knows it has lost the ability to start any workloads.
Yeah.
You have to check the runtime service logs, just like you check the kubelet logs.
Any broken link breaks the node.
Exactly.
And step 5, which is crucial if you are dealing with those pressure conditions, is verifying the physical limits yourself. You drop into the Linux command line and run df-h to check the actual disk space, or run free-m to check the physical RAM. You are confirming what Kubernetes is complaining about.
This step-by-step process highlights something every administrator needs to grasp. Do you really understand the architecture of a worker node?
Yeah, it's so important.
The kubelet is the absolute core component. It is the translator between the physical server's resources and the abstract Kubernetes API. If you understand how the kubelet functions and fails, node troubleshooting shifts from feeling like magic to being incredibly straightforward mechanical debugging.
Let's assume we followed that checklist. We SSH'd into the node, we found a runaway log file that was causing massive disk pressure, we deleted it, we restarted the kubelet, and the node transitions back to green. It is ready, the foundation is stable.
Success.
But wait, your pager is still going off. The applications are still crashing, and users are still angry. We have to move up a layer in the architecture from the foundation of the nodes to the actual workloads. We need to talk about pod debugging.
Oh, yes. This is where you will spend the vast majority of your time and energy as an engineer.
Really? Why is that?
Well, pods are the smallest deployable units in Kubernetes, right? They are the actual logical homes for your application containers. And because they are where the custom code lives, they can fail in a truly surprising variety of ways.
Yeah, developers are creative. So we have what I am calling the big 6 pod status issues. These are the classic, notorious errors you will see glaring at you when you run a get pods command. Let's go through them methodically, starting with the one that seems the most benign, pending.
Pending's a fascinating state because the pod hasn't actually failed to run. It just hasn't been given permission to start yet.
Like it's stuck in a waiting room.
Exactly. It means the control plane has accepted the pod definition, but it hasn't been assigned to a node, or the assigned node hasn't finished setting up the network sandbox.
If I see a pod stuck in pending for 20 minutes, my brain immediately goes to resource constraints, like the deployment asked for 10 gigabytes of RAM, but the biggest node in the entire cluster only has 8 gigabytes of RAM.
That is the most common culprit. The control plane component called the kubectl looks at your pod's request, evaluates the available capacity across all the worker nodes, shakes its head, realizes the math doesn't work, and leaves the pod parked in pending.
So how do you verify that? Do you manually calculate the RAM on every node? That sounds awful.
No, you let the cluster tell you.
Yeah.
You run kubectl describe pod and scroll down to the events. The scheduler will explicitly log a failed scheduling event and tell you exactly why.
It's that specific.
Yeah. It will say 0 out of 5 nodes are available, 3 nodes have insufficient memory, 2 nodes have matching node selectors but lack the required tolerations. It gives you the exact math.
That's super helpful.
You solve it by either lowering your pod's resource request to fit the cluster or provisioning a larger node.
Simple enough. Let the scheduler do the math.
Next up on the big 6 is image pullback-off. I see this one constantly, especially in CI/CD pipelines.
It is incredibly common. Image pullback-off means the kubelet agent on the node tried to reach out to a container registry like Docker Hub or AWS ECR or your company's private registry to download the container image, and the request failed.
And the back-off part.
The back-off portion of the status just indicates that the agent hasn't given up. It is going to keep retrying, waiting a little bit longer between each attempt to avoid spamming the registry. When I see this, I usually assume the authentication is broken. I forgot to attach the image pull secret to the service account, so the node is getting a 401 unauthorized error from the registry. But that isn't always it, is it?
Authentication is a frequent issue, yes.
Yeah.
But if we are being completely honest, more than half the time I troubleshoot an image pullback-off, it is just a typo in the deployment YAML.
Seriously, just a typo.
Yes. An engineer typed Nginx version 1.2 instead of 1.2, say, or they misspelled the repository name. The registry is returning a 404 not found error because the image simply does not exist.
Wow.
Checking the exact spelling and tag of the image definitions is always the very first troubleshooting step.
A missing zero bringing down a production deployment. Classic. Yeah. All right, the third error is the most notorious, the one that haunts DevOps engineers' dreams. CrashLoopBackOff.
Yes. CrashLoopBackOff means we solved the scheduling problem, we successfully downloaded the image, and the container actually started running.
So it's a lie.
Briefly. But then the custom application inside the container crashed immediately. Kubernetes notices the primary process died, so it restarts the container. The application crashes again. The cycle continues indefinitely.
And the cluster uses an exponential backoff delay here, right? Waiting 10 seconds, then 20, then 40, up to a maximum of about 5 minutes. Why does it do that? Why not just restart it instantly every time?
It is a self-preservation mechanism for the node. Starting a container is a relatively CPU-intensive operation for the kubelet and the container runtime.
I see.
If you have an application that crashes in half a second and Kubernetes restarted it instantly, the node would spend 100% of its CPU cycles just tearing down and spinning up broken containers. The backoff delay protects the node's resources from a fundamentally broken application.
So if the application is broken, how do you debug a container that won't stay alive long enough for you to exec into it and look around?
This is exactly where you use kubectl logs with that -- previous flag we discussed earlier.
Right, the graveyard flag.
Exactly. Even though the container died, the kubelet preserves the standard output and error from that previous failed execution. You read the stack trace to see what fatal error the code threw right before it terminated.
But what if the logs are totally clean? Like the app says it started successfully, but it's still in a crash loop backoff. What then?
Then you are likely dealing with a misconfigured health check. Kubernetes uses liveness probes to determine if an application is healthy.
How does that work?
Let's say you configured a liveness probe to make an HTTP GET request to port 8080 on your pod every 10 seconds. But the developer updated the application to listen on port 9000.
Oh, that is devious. The application is completely healthy, sitting there waiting for traffic on port 9000. But the kubelet is pinging port 8080, getting no response, assuming the application is dead, and violently terminating it.
Exactly. The cluster's own health check becomes the murder weapon.
That is wild.
You have to check the probe configurations in the describe output to ensure they match the application's actual behavior.
Okay, fourth on the Big Six list is create container configurer. That is quite a mouthful of an error state.
It is verbose, but it is highly specific. This state occurs when your pod definition attempts to mount or reference a configuration object, specifically a config map, or a secret that simply does not exist in the cluster.
So the kubelet looks at the pod specification and says, I am ready to build this container, but you told me to inject a database password from a secret named DB credentials, and I cannot find a secret with that name in this namespace.
Precisely. It pauses the creation process because it refuses to start the container with missing configuration data.
So how do you fix it?
The solution is verifying your references. Did you create the secret in the wrong namespace? Did you misspell the config map name in the volume mount definition? It is almost always a mapping error.
All right, the final two statuses of the Big Six are closely related, and here's where it gets really interesting. We have killed and we have evicted. Just reading the names, they both sound like the pod is getting forcefully kicked out of the node.
They do sound similar.
But the underlying mechanisms triggering them are completely different, aren't they?
They are entirely different from a root cause perspective, and mixing them up will send you down the wrong troubleshooting rabbit hole for hours. Let's start with killed, which stands for out of memory killed. This happens when the individual pod itself gets greedy and breaks its own rules.
How so?
When you define a pod, best practice dictates you set a memory limit. Let's say you limit the pod to 500 megabytes of RAM. The kubelet configures a Linux C group on the host operating system, enforcing that strict 500 megabyte boundary.
Okay.
If your application has a memory leak and it attempts to allocate 501 megabytes, the Linux kernel's killer mechanism instantly steps in and terminates the main process with extreme prejudice.
So killed is a targeted assassination by the Linux kernel because the pod crossed its assigned boundary. The pod is the guilty party. What about evicted?
Evicted is when the pod didn't necessarily do anything wrong. It might be running perfectly within its limits, but the node it is running on is in critical danger.
Oh, this goes back to the foundation.
Exactly. This ties directly back to our node troubleshooting section. If the entire server hits that memory pressure or disk pressure threshold we talk about, the kubelet enters panic mode.
Because if the node runs completely out of memory, the whole server crashes, taking every pod with it.
Exactly. To save the ship, the kubelet starts throwing cargo overboard. It initiates an eviction sequence, proactively terminating pods to free up node resources.
Does it just pick at random?
No, it prioritizes killing pods that are using more resources than their baseline requests, or pods with a lower priority class. In this scenario, the pod is just an innocent victim of a crumbling foundation.
That is a crucial distinction for you listening. If you see killed, you need to look inward at the application code, fix the memory leak, or increase the pod's specific limits.
Right.
If you see evicted, looking at the application is totally useless. You need to look outward at the node conditions and figure out why the entire server is starving for resources.
Beautifully summarized.
Okay, so we understand the Big Six pod failures. Let's formalize this into the ultimate 5-step mechanical checklist for a pod not starting scenario.
Step 1. Gather the top-level status. Run kubectl, get pod, and append the pod name. Look closely at the status column. Is it one of the Big Six? That tells you which branch of the troubleshooting tree to walk down.
Step 2. Pull the medical chart. Run kubectl, describe pod, scroll past the configuration, and read the chronological events at the bottom. Is the scheduler complaining about resources? Is the kubelet failing to pull an image?
Step 3. Read the application's diary. Run kubectl logs on the pod. If it is in a crash loop, you must remember to use the -- previous flag to see the error that caused the termination.
Step 4. Check the foundation. Run kubectl, describe node on the specific server hosting the pod. Check the resource limits and pressure conditions to see if you are dealing with a systemic eviction or a scheduling constraint.
And step 5. Verify your variables. Run kubectl, get pod-o YAML, and pipe it to grep image to make absolutely certain you don't just have a stupid typo in your container image tag or your config map reference.
It is completely methodical. You don't guess, you just observe. If you follow those 5 steps in order, you will isolate the root cause like 99% of the time. But I want to talk about that 1% of edge cases. There's a technique for pod debugging called ephemeral containers. What exactly is that, and why do we need it if we already have kubectl exec to teleport into a pod?
It is a more advanced technique. designed to solve a very modern security problem.
Security problem.
Yeah, in the past, container images were basically full operating systems. They had package managers, bash shells, curl, and network diagnostic tools built in. If an app broke, you would exec in, open a bash shell, and run your tests.
Sounds convenient.
It was. But today, the industry standard is moving towards distroless container images.
Distroless meaning no distribution.
Essentially, yes. A distroless image contains exactly two things your compiled application binary and the bare minimum runtime dependencies required to execute it. Absolutely nothing else.
Wow, really nothing else.
There is no bash shell. There is no package manager. There is no OLS command to list directories.
Because if a hacker compromises the application, they land inside a container that has zero tools for them to use to pivot and attack the rest of the network. It massively reduces the attack surface.
Exactly. It is fantastic for security, but it is an absolute nightmare for debugging.
I can imagine.
Right. If a distroless application starts returning network errors, you cannot kubectl exec into it and poke around because there is no shell binary for the exec command to attach to. The command just fails.
You are locked out of your own crime scene. So how do ephemeral containers solve this?
Kubernetes allows you to dynamically attach a temporary secondary container to an already running pod. This is an ephemeral container. You can define this container to use an image packed full of debugging tools, network sniffers, curl, bash shells.
Wait, if it is a separate container, how does that help debug the broken application container? Aren't they completely isolated from each other?
That is the genius of the design. When you inject an ephemeral container using the kubectl debug command, Kubernetes runs it inside the exact same Linux namespaces as the broken application container. They share the same network stack, they share the same process namespace.
Oh, wow. So it's like bringing your own specialized, fully stocked toolkit into a locked room, plugging it into the wall, doing all your diagnostics, and when you are done, you pack up and the temporary container disappears without permanently changing the pod's YAML template.
That's exactly it.
That is brilliant engineering.
Okay,
let's say the nodes are healthy. The pods are finally running and stable. They are not crashing. The logs look clean.
a brief moment of peace.
Very brief. Because, wait, your pager goes off again. The users are still getting errors, the applications cannot talk to each other, and no traffic is getting into the cluster from the internet. The organs are healthy, but the blood isn't pumping. We need to check the cluster's arteries, which are the networking and services.
Service and networking troubleshooting often feels like dark magic to engineers because it is largely invisible.
It totally feels like magic.
Right, you can't just exec into a network packet and look at it. But just like pod scheduling, there is a strict mechanical logic to how Kubernetes routes traffic via IP tables and virtual networking rules.
Let's start with service debugging. A service in Kubernetes is an abstraction, right? It is supposed to provide a stable, unchanging IP address and a DNS name for a group of dynamic pods that might be constantly dying and changing their own IP addresses.
That's the goal of a service, yeah.
So the first issue we need to troubleshoot is when a service has no endpoints. What does that actually mean under the hood?
To understand no endpoints, you have to understand how a service finds its target pods. It uses a label selector.
A label selector.
Yeah. When you create a service, you tell it, route all incoming traffic to any pod in this namespace that has the label app equals front end.
And then what does it do?
The control plane constantly scans the cluster for pods matching that exact label. When it finds them, it takes their individual pod IP addresses and adds them to a list. That list of IPs is called the service's endpoints.
So if you run a describe command on a service and the endpoint section is completely empty, it means the service is scanning the cluster, looking for that label, and finding absolutely nothing. It is completely blind.
Exactly. And the vast majority of the time, this isn't a network failure. It is a human mapping error.
TechGo strikes again.
Always. You labeled your pod app equals web, but the service was configured to look for app equals front end. They're sitting right next to each other in the cluster, perfectly healthy, but the service ignores the pod because the tags don't match.
It is like a sorting hat looking for the wrong name. The solution is simple. Compare the pod's labels to the service's selector block and make sure they are an identical, case-sensitive match.
Always check your spelling.
Okay, what about the second common issue? Connection refused. You check the endpoints, they're populated, the service clearly sees the pod's IP address. But when another microservice tries to send traffic to it, the connection just bounces off.
A connection refused error almost always points to a port mismatch. A Kubernetes service definition has two distinct, crucial port configurations. There is the port, which is the external port the service itself is listening on to accept incoming traffic.
And the other one?
And then there's the target port, which is the actual port the application inside the container is actively listening on.
So if my Python application is configured to start up and listen on port 8080, but my service's target port is accidentally configured to route traffic to port 80.
The traffic hits the service forwards it to the pod on port 80, but there is no process listening on port 80 inside the container.
So it just drops it.
The network stack of the container says nobody is home here and actively rejects the packet. Connection refused.
You are literally throwing the packet at a closed door. So the checklist for a service not working is methodical.
Definitely. Number 1, verify the service definition actually exists.
2, check the endpoints to ensure the label selectors actually discovered the pods.
3, validate that the target port maps exactly to the container's application port.
4, exec into a different pod in the cluster and try to curl the IP directly to rule out external network issues.
And step 5 is checking your network policies.
Network policies, how do those break things?
Well, network policies act like internal, software-defined firewalls between pods. A security engineer might have deployed a policy that explicitly blocks traffic from the back-end namespace to the front-end namespace. The service is configured perfectly, but the kernel-level firewall drops the packet intentionally.
Oh man, that's tricky.
Very tricky.
Okay, that covers the service objects themselves. But what if the service is configured flawlessly? The labels match, the ports map, no firewalls are blocking it, and things still aren't talking. This is where we move from service layer troubleshooting down to the underlying network troubleshooting.
The deep network layer.
Yeah, and the single most common culprit here is DNS. If I'm trying to reach a service by its internal name, like database.default.svc.cluster.local, and it just times out, DNS resolution is failing.
DNS issues will bring a cluster to its knees faster than almost anything else. Kubernetes has a built-in DNS server, usually a component called core DNS, running as a set of pods in the kube system namespace.
Okay.
Whenever an application tries to talk to a service by its URL, it first has to ask core DNS to translate that URL into the service's cluster IP address.
If the resolution fails, it means either the core DN pods are crashing or the kubelet failed to inject the correct DNS server IP into your application pod's network configuration file. But how do you isolate that? If a developer tells you, hey, my app can't find the database, how do you know if their code is broken or if the cluster's DNS is actually down?
You have to isolate the variable by testing the DNS system directly from within the network namespace of a pod. You can deploy a temporary debug pod that has networking tools installed, exec into it, and run a command like nslookup or dig against the service name.
So you run nslookup_database.default. If it returns an IP address, the DNS is fine, and the developer's application code is the problem.
Yes.
But if nslookup throws a timeout error, the cluster infrastructure is actually broken.
Exactly. And if nslookup fails, your next step is to troubleshoot the core DNS pods themselves using the exact same Big 5 toolkit we started with. You check their logs, you describe them to see if they are killed, you check if their endpoints are populated.
So you troubleshoot the cluster's internal network tools exactly the same way you troubleshoot your own applications.
Yep, it's pods all the way down.
Okay, what about external traffic? What if a pod needs to hit a public Stripe API on the internet to process a payment, and the request just hangs and times out?
When outbound external traffic fails, it usually points to a routing issue on the physical worker node or a restrictive egress network policy. Often, it involves a misconfiguration in NAT, network address translation.
Ah, NAT.
Right. The pod has a private internal IP address. To talk to the internet, the node has to translate that internal IP into the node's public IP using IPTABLE's rules.
And if those break?
If those rules are corrupted, the packet leaves the pod, hits the node's network boundary, and gets dropped before it ever reaches the external router.
And the reverse of that. What if external traffic from the internet cannot get inside the cluster to reach your web servers? This usually involves an ingress object, right?
Yes. An ingress controller is essentially a smart reverse proxy, often Nginx, sitting at the very edge of your cluster. It inspects the incoming HTTP request URL, looks at the path, and routes it to the correct internal service. If ingress isn't routing traffic, you have to trace the path backwards mechanically.
Trace it backwards. So first, you verify the DNS record of the domain points to the load balancer. Then you check the load balancer points to the ingress controller pods. Then you check the ingress resource definition. Did someone put a typo in the host name or the routing path? Does the path point to a service port that actually exists?
Precisely. It is a chain of custody for the packet. You have to verify every link from the external edge down to the pod container port.
Now, I have to ask about this last networking point because it is the foundation of it all. CNI plugin issues.
The CNI.
Right. CNI stands for Container Network Interface. It is the core software component like Calico, Flannel, or Cilium that actually wires up the virtual network cables and assigns IP addresses to pods. What happens when the CNI itself is broken?
When the CNI fails, the networking layer doesn't just act weird. The entire pod lifecycle grinds to a halt in a very specific, recognizable way. You'll see pods get completely stuck in the container creating state.
Wait, stuck in container creating? Why wouldn't they be stuck in pending?
Because the scheduler already did its job. The control plane found a valid node and assigned the pod to it. It is no longer pending. But when the queuelet on that node receives the order to start the pod, the very first thing it has to do is build a network sandbox.
Okay, so it asks the CNI for help.
Exactly. It sends a request to the CNI plugin saying, I need a virtual interface and a unique IP address for this new pod.
And if the CNI plugin is crashed or misconfigured, it never replies. It never hands out the IP address.
Exactly. And the kubelet is programmed to wait. It will not attempt to pull the image or start the application container until the network sandbox is fully initialized. So the pod just hangs in container creating indefinitely.
If you are looking at your terminal right now and you see 20 pods deployed across multiple nodes all stuck in container creating, your gut reaction might be to check the application code or the container registry. Don't. Stop and look at your network plugins.
Yes, look at the plugins. Check the logs of the CNI pods in the kube system namespace. Look at the kubelet logs via journal.tl to see if it is screaming about network initialization timeouts.
If we pull back and look at the bigger picture of cluster networking, you have to appreciate the sheer complexity of the layers.
It's mind-boggling sometimes.
Right. The application needs to listen on a port. That port must be exposed by a service. The service must be discoverable via core DNS. The traffic must be allowed by network policies, and it all routes over the virtual interfaces managed by the CNI. A failure at literally any one of those layers breaks the connection.
Any single point of failure.
I want you listening to just absorb that for a second. Think about the mechanical steps involved just to get a single packet of data from point A to point B in a Kubernetes cluster. You have iptables rules, virtual bridges, DNS lookups, label selectors, and NAT translation. It is an absolute miracle it works at all.
It really is.
And it really highlights why you cannot rely on guesswork when a network fails. You must use a methodical, layer-by-layer checklist to isolate the exact point of failure.
Which brings us to the next challenge.
Exactly. Okay. The network is flowing, our apps are communicating, but we have a brand new problem. Every time our database pod gets rescheduled to a new node, it wakes up with total amnesia. All the data is gone.
The worst.
We have a storage issue. The memory of the cluster is failing.
Storage in Kubernetes is notoriously tricky to troubleshoot.
Why is that?
Historically, containers were designed to be stateless and entirely ephemeral. If a web server container died, you didn't care about its local file system. You just spun up a new one.
Right. Cattle, not pets.
Exactly. But as Kubernetes matured, we started running stateful workloads, databases, message queues, file servers inside the cluster. And those require persistent storage that outlives the lifecycle of a single pod.
The primary mechanism for achieving that persistence is the PVC, the persistent volume claim. Our first storage troubleshooting scenario is PVC stuck in pending. Now, mechanically, this sounds exactly like a pod stuck in pending.
It is a very similar conceptual model. A persistent volume claim is basically a resource ticket. It is your pod saying to the cluster, I need a 50 gigabyte hard drive backed by fast SSD storage.
And if it gets stuck?
If that PVC object gets stuck in the pending state, it means the control plane cannot find or cannot dynamically create a physical storage volume, a persistent volume, or PV, that satisfies the requirements of that claim.
If you are running in AWS or Google Cloud, Kubernetes is usually configured to talk to the cloud provider's API and provision those disks automatically, right? Why would it fail to create it?
There are a few common failure points. First, the storage class might be misconfigured. A storage class tells the cluster which provisioner to use, like the AWS EBS driver. If the driver is broken, the provisioning fails.
What else?
Second, it could be an IAM permissions issue. The cluster's service account might not have the correct cloud provider roles authorized to physically create block storage.
Or it could be a configuration mismatch. Like, you asked for an access mode of read-write-many, meaning you want multiple pods on different nodes to mount the disk simultaneously. but the underlying physical storage class only supports read-write once, meaning it can only attach to a single node. The cluster realizes it cannot fulfill your specific contract, so the claim just hangs in pending.
To debug that, you use the exact same logic as pod debugging. You run kubectl, describe PVC, and read the events. The storage provisioner will log a detailed error explaining exactly why the Cloud API rejected the request for a new disk.
Okay, next scenario is pod cannot mount volume. The PVC successfully bound to a volume. The physical disk actually exists in the cloud, but the pod is throwing a timeout error and refusing to start.
This is a classic distributed systems problem, and it happens frequently with cloud block storage when a pod crashes and is rescheduled to a completely different worker node.
Walk me through that.
Let's say your database pod was running on node A, actively using an EBS volume. The pod crashes, and the scheduler decides to spin up the replacement pod on node B.
But cloud block storage disks, by physical design, can usually only be attached to one virtual machine at a time.
Exactly. The control plane sends an API call to the cloud provider to detach the disk from node A, and another call to attach it to node B. But if node A is in a degraded state, or the cloud API is sluggish, the disk might not detach cleanly. It gets stuck.
Oh man, so then what?
When node B tries to mount it, the cloud provider rejects the request because the disk is still locked to node A.
The pod on node B will just sit there, throwing multi-attach errors or timeout warnings. And unfortunately, the fix usually involves leaving Kubernetes entirely, logging into your AWS or Azure console, and forcefully detaching the stuck volume from the dead node so the new node can claim it. It is incredibly annoying.
It's the worst part of stateful sets.
All right. The third scenario is the amnesia problem: volume data not persisting. The pod restarts, the disk mounts successfully, but all the database records are just wiped clean.
When data vanishes upon a restart, it is almost always a configuration error in the deployment YAML authored by the developer. They might have accidentally configured the pod's volume mount to use an empty dir volume instead of pointing to the persistent volume claim.
What exactly is an empty dir?
An empty dir is a type of volume that is physically tied to the exact lifecycle of the pod it is attached to. It provisions temporary scratch space on the worker node's local file system.
So it's not meant for long-term storage?
Not at all.
Yeah.
It is great for caching or holding temporary files while a pod processes them. But the moment that pod is deleted or evicted, the kubelet reaches in and intentionally wipes the empty dir completely clean. It is the opposite of persistent storage.
So if you put your database data directory inside an empty dir, you are guaranteeing data loss on the next pod restart.
100%.
You have to check the pod's YAML specification and ensure the volume mounts are actively referencing your persistent claims, not temporary directories. And finally, we have disk pressure on node. Wait a minute. We covered this in section 2 when we talked about the foundational node troubleshooting. Why is it appearing again in the storage section?
Well, if we connect this to the bigger picture, storage in Kubernetes isn't just about saving your database records to a cloud volume. It's a tightly coupled ecosystem. The worker node itself has a finite amount of physical, local hard drive space.
Right, where it stores the container images and the application logs.
Yes. And if a developer writes an application that goes rogue and starts dumping gigabytes of debug logs to standard output, or it starts writing massive temporary files to the container's root file system, it isn't using a cloud volume. It is consuming the physical local storage of the worker node.
Ah, and when that local storage fills up, it triggers the disk pressure condition on the node.
Exactly. A storage failure at the application level rapidly cascades into a systemic node failure.
That's a nasty domino effect.
It is. The node panics. It realizes its drive is full, so it starts an eviction sequence, aggressively terminating pods, even completely innocent, unrelated pods, just to reclaim disk space and save the operating system from crashing.
That is a phenomenal example of why you have to understand the whole stack. The application's runaway storage greed destroys the node's foundational stability, which brings down completely unrelated services. You have to monitor your local ephemeral storage usage just as aggressively as your persistent cloud volumes, using resource limits to prevent any single pod from consuming the whole disk.
Monitor everything.
Okay. We have covered a massive amount of ground. We fixed the physical nodes, we debugged the application pods, we traced the network routing, and we secured the storage volumes. Everything at the worker layer looks pristine, the servers have space, the network routes are clean.
Deep breath. We're almost there.
But you open your terminal to check the status one last time, you type kubectl get pods, you hit enter, and the terminal just hangs. The cursor blinks, and then it throws a cryptic connection timeout error. You try to check the nodes. Timeout. The cluster is completely ignoring your commands.
The dreaded timeout.
We are facing the ultimate apocalyptic nightmare scenario. The control plane is failing. We are operating on the brain of the cluster itself.
This is the scariest part of troubleshooting for many engineers. The worker nodes do the heavy lifting, but the control plane is the nervous system.
What happens when it goes down?
If the control plane goes down, you lose all ability to manage, observe, or alter the cluster. The workloads that are already running on the worker nodes might actually continue to serve traffic perfectly fine, but you cannot update them, you cannot scale them, and if a worker node dies, the control plane isn't there to reschedule the pods. You are flying completely blind without instruments.
We need to dissect the two absolute core components of the control plane, the API server and etcd. Let's start with the API server. If it is not responding to our commands, what exactly is happening?
The API server, the Kube API component, is the singular gateway to the entire cluster. It is the only component that is exposed externally.
Everything goes through it.
Everything. Every single kubectl command you type on your laptop is translated into an HTTP REST request and sent to the API server. Every worker node reporting its status sends that status to the API server. The scheduler, the controllers, they all talk exclusively to the API server. If it is down, the cluster is effectively deaf and paralyzed.
I always compare the API server to the front desk receptionist at a highly secure, massive corporate building. No matter who you are, whether you are the CEO or a delivery driver, you have to talk to the receptionist first.
I like that.
If the receptionist falls asleep at the desk, nobody gets into the building, no internal messages are delivered between floors, and the entire operation gridlocks.
That is a highly accurate analogy. And why would the receptionist fall asleep?
Yeah, why?
Well, in a Kubernetes context, the Kube API component runs as a static pod on the control plane nodes. It might be experiencing severe resource exhaustion. If you have a massive cluster with thousands of nodes constantly hammering it with status updates, it might simply run out of memory and get killed by the control plane's operating system.
But assuming it has enough RAM, what is the other major failure point?
The other major point of failure, and frankly the most common cause of control plane lockouts, revolves around certificates.
Certificates. We haven't talked about security certificates much at all yet.
We haven't, but they are the invisible glue holding the cluster together. Kubernetes relies heavily on mutual TLS authentication for every internal communication.
It's not just encryption.
Right. It is not just about encrypting the traffic. It is about verifying identity. The kubelet on a worker node needs a valid cryptographic certificate to prove who it is to the API server, acting like a corporate employee ID badge.
And the other way around.
Exactly. Conversely, the API server needs a valid certificate to prove to the kubelet that it is the legitimate control plane, not an imposter.
So what happens when those ID badges expire?
The system breaks down entirely. By default, if you used a tool like kubeadm to bootstrap your cluster, the control plane certificates are generated with a validity period of exactly 1 year.
Just 1 year?
Yes. If you do not have an automated process to rotate those certificates before the 365 days are up,
the certificates expire at midnight. The API server looks at its own expired badge, realizes it is invalid, and refuses to establish secure connections with anyone. It locks the front doors of the building.
Exactly. Certificate expiration is the silent killer of Kubernetes clusters. It ticks away for a year, you completely forget about it, and then one day the entire cluster abruptly dies.
How do you even fix that if you're locked out?
To troubleshoot this, you have to SSH directly into the control plane node, drop down to the host OS tools we discussed in Section 1, and read the API server logs from the /var/log/pods directory.
Or use journal clock.
Or use journal clock if it runs as a system service. The logs will explicitly scream about by 509 certificate expiration errors. You have to use manual command line tools to regenerate the certificates and restart the static pods.
Okay, so we SSH into the control plane, we rotate the certificates, we wake the receptionist up, the API server is online and accepting connections. But what if the receptionist is awake, but the filing cabinet they used to store all the corporate documents is on fire?
That brings us to the final, most critical component, etcd.
Yes. etcd is the true heart of Kubernetes. It is a highly available distributed key value store. It is the highly secure filing cabinet sitting behind the receptionist's desk. The ultimate source of truth.
It is the ultimate singular source of truth for the entire cluster. Every configuration file, every pod state, every secret, every service definition, it is all stored in etcd.
The API server doesn't actually store anything itself.
Nothing. The Kube API component is completely stateless. It relies entirely on etcd to know what the cluster is supposed to look like. When you create a deployment, the API server validates the request, but then it immediately writes that deployment configuration into the etcd database.
So if etcd experiences data corruption or the etcd cluster itself becomes unhealthy, what happens to the Kubernetes cluster?
It is catastrophic. etcd operates on a distributed consensus algorithm called RAFT. In a highly available control plane, you usually have 3 or 5 ECD nodes running.
They vote, right.
They constantly vote to elect a leader and agree on the state of the data. This requires a mathematical quorum, a strict majority. In a 3-node cluster, 2 nodes must agree to form a quorum. If you lose 2 of those 3 nodes, say due to a network partition or hardware failure, you lose quorum.
And when it loses quorum, does it just serve up old data?
No, to protect the integrity of the database and prevent split-brain scenarios where different nodes write conflicting data, a fragmented etcd cluster instantly stops accepting all write requests.
So the entire Kubernetes cluster goes read-only.
At best, it goes read-only. You can run get commands to see what is running, but you cannot deploy any new pods, you cannot delete old pods, you cannot update configurations. The API server tries to write the changes to the filing cabinet, but etcd rejects them.
And at worst?
At worst, if the data is actually corrupted, it returns errors for everything. The cluster becomes a complete zombie.
How do you even begin to troubleshoot that? You can't use kubectl because the API server can't talk to the database.
You have to bypass Kubernetes entirely. You SSH into the control plane nodes and interact directly with the etcd cluster using its own dedicated command line tool called etc.it.
And what do you do with that?
You have to pass it the specific cryptographic certificates it requires for authentication, and you run commands to check the endpoint health, check the cluster membership list, and verify if the cluster has successfully elected a leader.
And what if the diagnosis is terminal? What if the disk holding the etcd database experienced hardware failure and the data is completely corrupted?
If the data is corrupted and quorum cannot be restored, your only solution is a disaster recovery operation. You have to wipe the existing database and restore the etcd state from a backup snapshot file.
This highlights something critical. Taking automated, frequent, cryptographically secure backups of etcd using the etc.xctl snapshot save command is arguably the single most important administrative task for a Kubernetes operator.
Without a doubt, if you lose the worker nodes, you can spin up new ones. If you lose the API server, you can restart it.
But if you lose the etcd?
If you lose the etcd data and you do not have a backup snapshot, you have lost the cluster entirely. Every configuration is gone. You have to rebuild the entire infrastructure from scratch. It is a resume-generating event.
That is incredibly sobering. The brain goes down, the memory is wiped, and it doesn't matter how healthy the limbs are, the organism is dead. Okay. Let's take a collective breath here. We have covered an immense, truly staggering amount of ground today.
We really did.
We started at the surface level with the Big 5 toolkit, mastering how to read the medical charts with describe and view the surveillance cameras with events. We dropped down to the physical foundation, diagnosing disk pressure and crashing kubelet agents on the worker nodes.
And then into the pods.
Right. We moved up into the application workloads, unpacking the precise mechanics behind CrashLoopBackOff, the difference between killed and evicted, and how to inject ephemeral debugging containers. We traced the complex network arteries through label selectors, core DNS, and CNI plugins.
Yep.
We fixed storage amnesia by tracking persistent volume claims and cloud block storage attachment lifecycles.
And finally, the control plane.
Yep. We performed brain surgery on the control plane, troubleshooting mutual TLS certificate expiration in the API server, and quorum loss in etcd.
It is a massive technical journey. But if you take away one core philosophy from this deep dive, let it be the power of a structured layer-by-layer approach.
Don't just guess.
Exactly. When the pager goes off at 3 in the morning, do not panic. Do not start restarting random pods, hoping the problem goes away. Trust the checklists. Check the top-level status, describe the events, read the application logs, verify the node foundation, and follow the chain of command systematically from the application code down to the bare metal.
And if you do that,
armed with an understanding of these mechanical relationships, you aren't just prepared to pass the CKA exam. You are genuinely equipped to isolate and resolve real-world production outages with surgical precision.
So what does this all mean for the future of your day-to-day operations? We have spent this entire deep dive talking about how you, the human operator, can find and fix these issues manually. The detective work. But as you look at these highly precise, predictable patterns we just discussed, a label mismatch causing an empty service, a missing config map triggering a configuration error, a node slowly running out of disk space. Ask yourself a question. How much of this manual troubleshooting can you automate?
Now that is the real goal.
If the Kubernetes control plane already knows a pod is trapped in a CrashLoopBackOff, and it already knows how to generate the specific events describing exactly why it is crashing, what is physically stopping you from building a system that parses those events and heals itself before you ever even receive the pager alert.
Nothing is stopping you.
Maybe by writing a controller that automatically rolls a failing deployment back to the previous known good version, or a script that automatically expands a cloud disk volume when it hits 80% capacity. It is something profound to mull over before your next late-night on-call shift. Can you use the mechanics of Kubernetes to engineer these manual checklists right out of your job description?
Abstracting away the manual toil to focus on architecture. That is the true evolution of a DevOps engineer.
Thanks for joining us in the trenches on this deep dive. Stay curious, stay tactical, and we will catch you next time.
Goodbye.